a couple of important breakthroughs in machine learning, fortunately, after somewhat a long and tedious time where not much was happening, and every model pre-trained on some amount of usually labeled data was able to perform only a narrow range of tasks, so not really transferable. So the transferable learning is finally possible. And we have the so-called foundation models that are artifacts that is a living proof that transferable learning to some extent works. So one of the central messages I would like to make is that we have still usually this notion of, okay, there are hyperscalers. They can work on this problem of actually researching and building foundation models, and everybody else, including us in academia, should concentrate in post-training and try to figure out the transfer procedures. But we cannot really touch the pre-training because it's so expensive, and only a few people have expertise in this, so let's leave it out. So I think this is not true, and I hope with our work and work by others, it was shown meanwhile that also in academia we can have an idea how to progress on getting the foundation models better by also studying pre-training. So what is the way to systematically improve there? The foundation models exhibit scaling laws. This is empirically quite a clear thing across various learning procedures. Here only shown old paper and model scaling laws for language modeling only, but meanwhile across different types we can see the same behavior, that if you invest in compute data set size, model scale during the pre-training, you have this predictable increase in core capabilities, so generalization as hopefully measured well by various metrics here, only shown in the case of a test loss. So meanwhile, we can measure it also on downstream tasks to make this claim somewhat more substantiated. And the scaling laws are not only giving you the idea that your learning procedure improves without changing algorithmic core, it can also make quite precise predictions about what do you have to do on a certain scale to achieve a certain level of targeted performance. So what would be your model size? What would be the amount of data that you need to take? So it also leaves you not blind anymore with respect to the properties of the procedure that you have to do to make model capable. So now the problem was, and still to some extent is, that both studying pre-training as a procedure and also studying scaling law derivation is resource hungry and also requires certain type of expertise that was available a few years ago only in some closed research labs in the industry. So important large, specifically large foundation models were closed to academia, public research, and data sets specifically necessary to train those models were all closed, but actually one important ingredient that is required to perform the kind of research. So a majority of the actual important artifacts for core machine learning, strong foundation models, were non-reproducible by any independent party, and were actually intransparent artifacts, and not really what we have to get in science. This led to rise of different grassroots research communities that were operating across boundaries of scientific organizations that were already established. So to out of despair in the situation, to actually then enable the study of foundation models in open source, different components required to do so. So LUTHER-AI appeared in US around 2019, maybe in 2020, focused on language modeling, creating a very important data set pile that inseminated a lot of follow-up work. Big science in Europe actually ignited in Paris around efforts by Hugging Face to coordinate people to try to replicate GPT-3 kind of model back then, which led also to a number of works that are deserving the label open source, being data, training, the actual models are all in open form. And LAION appearing in Germany in 2021, focusing from the start on multimodal foundation models, so language vision, language audio, so that in current situation we have some of these pipelines that are required for the performing research and foundation models, and actually building them being fully open and reproducible. So example of LAION work here, specifically data sets like LAION, Re-LAION, 400 million 5B, follow-up works, data comp 1B, enabled training of models like OpenCLIP, OpenFlamingo, and importantly also established reproducible open benchmarks that any independent party can take and then evaluate the same way to validate the claims behind any research based on such a pipeline. So what can you do with it to enable progress in foundation model research and construction, so to speak? So you can derive fully reproducible scaling laws that show all the important characteristics, if derived correctly, of the learning procedure that you are interested in. Also, first of all, proving the claim that you have a foundation model type, for instance, for CLIP, that was not clearly shown in original work. We not only reproduced the observations from the original OpenAI work on CLIP, but actually derived scaling law that was then validating the claim. Yes, we have a foundation model here that improves with increase in compute during the pre-training. And importantly, though, we can make all of the sudden comparisons, for example, here between two data sets, because we align the algorithmic procedure behind the pre-training very much one-to-one, and the only difference that is remaining is the data set. So in blue, you see not a scaling law, a scaling trend for the closed data set used to train CLIP by OpenAI, VIT, 400 million. And in red, you see the same procedure executed on LAION 400M and 2B, which tells you that for this particular type of downstream task, namely zero-shot ImageNet 1K classification, you have at the smaller scales somewhat a small gap in favor of LAION, but then you see that at the larger scale, the VIT data set is more favorable. You have one particular task where you can decide what data now you choose for your pre-training to have specifically for classification, stronger performance at larger scales. So now for a different type of task, it can look differently. Here for zero-shot retrieval on MS, evaluated on MS Coco, you see a reverse picture where the LAION data turns out to be beneficial across scales, and VIT is lagging behind it, also having arguably here, cannot say have estimated scaling trend correctly on the 3 points available for the blue, but there is a hint that scalability is also better with using LAION data. So important here is that you don't only have a validated comparison, but you can be sure that the numbers of performance that you obtain for your own learning procedure are now matchable to the strong reference that you took to compare to. So there are not only just some few isolated points you make comparison with, you have a full trend. And you can claim that, yes, okay, you are able to match the pre-training procedure to the one that is the closest available, that is the strongest available state of the art. So as an encouragement, it is possible to drive the training also in academia without raising hundreds of millions of euro and huge amounts of resources for the compute, which we had to do on public funded supercomputers as well. But so you can do it in academia with the right organizational structure and right people who have the expertise, binding them across institutional boundaries, making them work together, and you can have the strongest model available for open studies as a result. So it is very important to have this comparison fair, so that you do not cheat on yourself, that you don't put the test downstream tasks into the training set. You deduplicate. So we did a work to deduplicate line against ImageNet, for instance, against MS Coco. We have a compute alignment to make sure that the comparison is exactly talking about taking the very same amount of compute to train the model, so that we can say that the learning procedure, yes, it matches or even outperforms the one that was the strongest state of the art. So we can have open frontier labs that are operating in academia as well. As an additional validation that these successes are possible, you can also have a look on numbers of usability indicators, numbers of downloads and Hugging Face, not only for LAION artifacts, but also for ELSA or other AI. So for OpenCLIP, there are hundreds of millions of total downloads of the pre-trained models, still a couple of million downloads a month, even that the models are already old, so they're 3 years old, right? There are 10,000 of stars for the source code repository, so the community usage is also giving you the idea that these are successful attempts to deal with pre-training. So we do the same now with various strong collaborators. One of the very usual suspects here is Ludwig Schmidt, used to be at LNAI, University of Washington. Now he's at Stanford, so very famous for Datacom series of works. So he has Datacom LM for language modeling, where we don't derive a full scaling law, but estimate scaling trends. And you can also see that you can actually grab from common crawl data sets that are open and strong enough to have a pre-training procedure that leads you in the realm of performance of the strongest available open weight models that are, say, LAM or QN. It is important to have this not just the strongest models at the end, but the references to compare to. This is what we also now do with OpenViewer LLM and OpenSci Collective, that is a branch of LAION dealing with incepting stronger reasoning and generalization in the models. So here's a piece of work that shows that when you go across various scales and touch some of the important reference data sets indicated in different colors, then you can have an idea for a training run on somewhat already substantial scales, going here up to 300 billion tokens. And importantly, after such runs, you don't just have a glimpse of how the learning behaves, but you can have now comparison across various reference scales and data sets to any procedure that you would like to claim as an improvement on the top of what already exists. So here you see indication very strong that Nemotron CC is a very good data set to work with. And if you would like to compose a new data set, well, you better measure it against such references available to be somewhat well-informed whether you're on the right track with your attempt or not. So somewhat stopped reacting to my instructions. Hold on. Let's see whether it will be better.
We can mute the participants.
Okay. It goes again. So you can derive from such reference experiments also scaling trends. The scaling trends allow you then to see how well you stand with your attempt to improve on the current state of the art across different scales, and see whether, if you get a slope that is not good enough compared to the references, you should improve the learning procedure to be more scalable. So we do the same now for incepting stronger reasoning into models. Again, work together with Luke Schmidt on gathering data sets composed of synthetic reasoning traces generated either by R1 or by QWQ32B, open thoughts data set, and then resulting models, open thinker. Here you can now measure the scaling trends in the post-training, which is also important. So the pre-training doesn't stand alone, giving you the base models. You have also to check up what happens if you attempt to post-train them and how you benefit there from the increasing amount of data scale, for instance, during the post-training. So here, this is also a good procedure for a sanity check of your attempt to improve on the current state of the art in the pre-training. If you have a look what happens then further with downstream procedures, are they working as expected compared to existing state-of-the-art references. So now another central part of the story I would like to tell here is so how to enable the systematic search for better procedures. I think we have quite a good evidence that this can be done well by full scaling law derivation, which avoids conventional some of the usual troubles with model learning procedure comparison. And the STOI example that I was also showing yesterday, so first of all, establishing the reference, right? And the reference would be here, the blue line, a learning procedure that have a certain behavior across scales. Now, again, putting the total compute on the X to have an idea, what do you get for that amount of compute invested in your pre-training, and then beginning to make interventions. Changes on the top of the existing procedure may lead you to the orange scaling law derivation. And you can now imagine what happens if you don't derive the scaling law and don't infer the trends, and just look at the smaller compute scales and the rather low absolute performance in this left part of the plot. So there you would see that the orange has a substantial gap to the blue, so being underperforming strongly the blue reference procedure, and you would may arrive to the wrong conclusion that the interventions you did to the blue are not worth it, and then you would just abandon them. But if you then derive the full scaling law, you see that there is this line crossing happening, which means that the intervention is actually leading to stronger scalable learning procedure, and it will be worse to take those to the large scale and obtain actually a stronger performant model in the actually relevant stronger absolute performance range and the right part. So we did this, we made this toy plot into a real study, looking at scalability of two important language vision procedures. Again, standard CLIP, contrastive only, and contrastive plus captioner, which is a Mammoth architecture. It could be also Coca. We took Mammoth because it seemed to be a more simpler architectural design, and we always prefer simple because there is some evidence that is also then leading to more scalable methods in the end. So, and here you see a result by deriving full scaling laws for the both model architectures on data count 1.4 billion. This story indeed happens that the CLIP architecture, the scaling law for it depicted in green, gives you the idea that on the smaller scales it has an advantage for this two type of tasks that I show here, the zero-shot ImageNet classification on the left and zero-shot retrieval MSCOC on the right. But then there is a crossing point from some certain critical compute threshold on the pre-training where you see Mammoth taking over. So again, if you would like to go to obtaining a strong model that performs better on the larger compute scales, you would better take Mammut according to this prediction, which would be rendered invisible if you don't derive these full scaling laws. So, and we can make sure that we can trust in this on help. You trust information. Accuracy is estimated, then together with confidence intervals gives you an idea about uncertainty behind your prediction. And if you fall with the actual measurements into these intervals and held out points, you can be sure, okay, what is predicted by the scaling law is the correct trend. So we can then also trust into the comparison based on this two fits shown before. You can then begin increase, so to speak, the consistency of the comparison by validating it again with deriving the same scaling, the same type of scaling law using the same measurements across different conditions. So here, different data set, RE-LAION 1.5b, you see a very similar trend. So your confidence increases that the comparison makes even more and more sense. You can do now data set comparison. So 3 different data sets, now data comp, RE-LAION, and DFN. By looking at these 2 different architectures on the left, OpenCLIP, on the right, Mammut. So you see now a data set ranking that is a bit similar to what I have been shown for language modeling in the form of a full scaling law, though. So now we are not just talking about some isolated reference scales, but this is a fully derived scaling law comparing the data sets via full scaling law derivation. Again, showing that there is one preferred data set here, namely in yellow, the DFN, that gives you better performance across scales if comparing on downstream task of zero-shot ImageNet classification. And you can have a look at the different task type. So a lot of different task types, ideally, so that you make sure that the comparison trends are holding. So here for retrieval on MS COCO, again indicating that in yellow, DFN is a better data set to take for pre-training. So this comparison is not just an exercise of predicting what the procedure is capable of. We also take the prediction seriously and go and train a Mammut model on larger scales, obtaining indeed performance that is on par with strongest closed models available, and matching or outperforming the available open weights or fully open models that also have the data available. So it is worse to derive the scaling laws not only because to compare the procedure, but you actually have a pathway to a useful artifact that can be released and be useful for the community as a follow-up research building block that is strong enough in addition to see interesting function. So all of this, of course, depends on how well you are able to claim that the downstream task performance that you take as a score to do measurements for scaling law derivation has indeed anything to do with the generalization performance of the models. And this is another line of work that we are pushing, so establishing evaluations that indeed would measure the generalization capability more faithful than the current standardized benchmarks are able to do so. The hint that these benchmarks are not reflecting the model capability to generalize very well comes from this part, from this line of work of ours, where we test language and reasoning models on a very simple, as you can see, problem kind that we call Alice in Wonderland problems, because there is somebody called Alice featured in there. And the problem has a very short natural language formulation. I guess even elementary school level people would be able to handle this. And what we see, though, that if you begin to vary this problem in a very natural way, so not adversarial, not playing with some weird wording tricks, but just changing the natural numbers in this problem template, you see strong fluctuations in performance across different variations of this problem, even in the strongest available reasoning models. So if you have a look at DeepSeek R1, if the claims of strong performance on Olympiad level or graduate level math, natural science task is true, you would probably expect that whatever absolute level of performance should be on this problem, probably actually 100%, but it should not fluctuate wildly only because you change just the numbers in the problem formulation. But what you see that on some variations, like in red, it reaches indeed almost 100% correct response rate to the question, but on some variations, like in blue, it falls almost down to 0.3. So how can it be? It can be only if generalization capability, namely, well, the ability to infer the problem structure, is in some way seriously jeopardized. So we need, so this is a tool to measure these weaknesses, and which indicates then that our benchmarks that attest to this model, the strong Olympiad level, graduate level problem solving, are not really reflecting the capabilities correctly. So the path forward for us as a community, I suggest, is that we indeed go and use scaling law derivation to measure capabilities of different foundation model components that we can stack together in larger systems like indicated here, so that we take actually the verifiably strong components to work with and obtain also then follow-up scaling laws for these larger systems in the same way, which can lead us then to the multimodal foundation models with stronger generalization as predictably stronger generalization as we have currently. So in dreams, a moonshot could be indeed something like a multimodal foundation action model family that could serve also as a kind of open source operation system, both for robotics and for autonomous agents. I mean, examples like OpenVLA are already out there. We just need to make this story a bit more robust. And for this, we need serious amount of compute. It has to be clear that all this work done by LAION was only possible because we went and applied for a heavy compute grants on public funded supercomputers. So we need to get routinized as a community to do this, and every research lab will be able to do this kind of research. So there is no, these claims of hyperscalers are the only people possible to do so. We can become hyperscalers with necessary amount of motivation. We can do a bit better. We could try to organize ourselves just by, for the resource acquisition. Why don't we create an OSFOMO alliance where the people who already built these models and already have know-how how to do it, Hugging Face, Black Forest Labs, Trial Labs, LAION, our partners from overseas, Together AI, Lure, so that we can actually agree a bit like the physics people working in CERN agree on some fundamental directions to dig in, and then the amount of compute can be justified by the importance of these directions reached in the consensus. And then we can study whatever scale we like. So again, it's just a matter of organizing us together and avoiding whatever trench fights that are also usual due to some political considerations, whatsoever. Right. So I hope I was able to bring some convincing messages that we can do it. LAION is an organization that is just relying on a lot of people. So Mariana Nijurina, as a core LAION researcher sitting here, can ask her whether this is actually true. So would like to acknowledge everyone who contributed to the success of this community, especially also Mehdi Cherti as a for senior researcher and Ludwig Schmidt as a long-standing collaborator, and everyone else who is having some time to spend on the LAION Discord server, and please join us to help research going forward. Thanks a lot for your attention.